The prediction of the molecular geometry of beryllium chloride gaseous phase using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure. Beryllium is found in the second group and second period of the periodic table. Beryllium will therefore have 2 valence electrons that can be shared in covalent bond formation. The chlorine atom is found in the 7th group and 3rd period of the periodic table. Chlorine then will have 7 valence electrons for bond formation. Beryllium, 2 electrons. Chlorine atoms, 7 electrons. The terminal chlorine atoms will form single bonds, and both of them will have 8 electrons, the electron octet. Beryllium, though, cannot have 8 electrons. Here we've got a typical example of the exception to the octet rule. Prediction of molecular geometry, we've got a central atom, beryllium, represented by A, 2 terminal atoms. No distortions in this molecule because we haven't got any lone pairs on the central atom. The molecular geometry will be the same as the electron pair geometry AB2, where we have got AB2 predict a linear molecular geometry. The bond angle, when we look at the atomic nucleus, which will now be chlorine going to nucleus beryllium going to atomic nucleus chlorine, the bond angle here will be 180 degrees. When we draw the molecular geometry of beryllium chloride, we use Cooper or Cowper structures. We have got beryllium, single bond to the chlorine atom. We introduce the lone pairs on the chlorine atom, but being a terminal atom, these lone pairs will not influence the molecular geometry. So that we have got a linear molecule, bond angle 180 degrees. The electron octet around beryllium can form when the beryllium chloride molecules form a polymer structure. When not in the gaseous phase, we find that the polymeric structure of beryllium chloride is formed by the dative covalent or coordinate covalent bond formation, where the chlorine atoms, the lone pairs on the chlorine atoms, will be donated to the open orbitals around beryllium. Here now we've got 2 dative covalent bonds, 2 single bonds, and also an electron octet around the central beryllium atom. The prediction of the molecular geometry of carbon dioxide using the VSEPR theory, valence shell electron pair repulsion theory, and we draw the Lewis structure first. Carbon is the central atom. It is found in the 4th group and 2nd period of the periodic table. It has got 4 valence electrons for covalent bond formation. Carbon can form single, double or triple bonds. It is the classical atom to form electron octets. Oxygen is found in the 6th group and 2nd period of the periodic table. It has got 6 valence electrons for covalent bond formation. It is a terminal atom. It can form either single or double bonds. Carbon with 4 valence electrons. Oxygen, 6 valence electrons. And because both of these atoms are found in the 2nd period, we can form only electron octets. We can suggest a Lewis structure where carbon is bonded with 2 double bonds to the 2 oxygen atoms. All the atoms now will have electron octets. The central atom A is bonded to 2 terminal atoms. There are no lone pairs on the central atom. The molecular geometry comes from the electron pair geometry AB2. AB2 predicts a linear molecular geometry, bond angle 180 degrees. We make use of Cooper or Kuiper structures to draw the molecular geometry. We've got a central atom, carbon, bonded with 2 double bonds to oxygen atoms. We predict a bond angle of 180 degrees, and we predict a linear geometry. The molecular geometry will depend on the position of the atomic nuclei in three-dimensional space. Atomic nucleus oxygen, atomic nucleus carbon, atomic nucleus oxygen will describe a linear molecular geometry. The prediction of the molecular geometry of the nitrile cation using the Vesper theory, valence shell electron pair repulsion theory, and to draw the Lewis structure. Nitrogen is found in the 5th group and 2nd period of the periodic table. Nitrogen will have 5 valence electrons that can be used for covalent bond formation. Oxygen is found in the 6th group, 2nd period of the periodic table, and will have therefore 6 valence electrons that can be used for covalent bond formation. The cation has lost 1 electron. The atom with the lower electronegativity will lose the electron. And our central atom, nitrogen, now will have 4 valence electrons instead of 5 valence electrons. The 2 oxygen atoms, though, will have 6 valence electrons. And we place brackets and the charge on the molecule. We see now if we propose a structure where we form 2 double bonds in the molecule, we can form the classical electron octet around each atom. 2, 4, 6, 8, nitrogen 2, 4, 6, 8, oxygen 2, 4, 6, 8. The electron pair geometry is determined by the central atom A, bonded to 2 terminal atoms, and because we have got no lone pairs around the central atom, we will have no distortions in our molecule. An AB2 electron pair geometry will describe a linear molecular geometry where we have got a bond angle of 180 degrees when we move from atomic oxygen nucleus to nitrogen nucleus to oxygen nucleus. We use Cooper or Kuiper structures to draw the molecular geometry. Nitrogen, double bond oxygen, lone pairs on the oxygen. The lone pairs on the terminal atoms will not cause distortions in the molecule. For the Cooper structure then, we write the molecular geometry linear. We indicate the expected bond angle. If we then look at the molecular structure, the linear structure is described by atomic nucleus, oxygen moving to nitrogen atomic nucleus, to atomic nucleus oxygen here, linear geometry, bond angle 180 degrees.